All right, let's dive in. Today, we're cracking open the ultimate recipe book. This is the one that explains literally everything around us. We're going to learn the fundamental ingredients and the absolute unbreakable rules that cook up the entire universe. So you ready? Let's get started. It's a huge question, one that people have been asking for, well, forever. If you just keep breaking things down into smaller and smaller pieces, where do you end up? What's the bottom line? What is all this stuff really made of? Well, stick around because we're about to find out. So, before we even touch the ingredients in our cosmic kitchen, we have to talk about the rules. And these aren't just suggestions, okay? These are the fundamental laws that govern how everything gets put together. They're the non-negotiables figured out by some seriously smart chemists a long, long time ago. Okay, meet two of the biggest rules in the entire recipe book. First up, we've got the law of conservation of mass from Antoine Lavoisier. Super simple idea. You can't create matter out of thin air, and you can't make it disappear. Then there's the law of constant proportions from Joseph Proust, which basically says that a pure substance always has the same ingredients in the same fixed ratio. No exceptions. Here's what that first law really means. Nothing is ever truly lost. Think about a log burning in a fireplace. It looks like it's disappearing, right? But it's not. All the atoms that made up that log have just rearranged themselves into ash and smoke and gases. If you could somehow trap all of that and weigh it, it would weigh the exact same as the original log. Wild. And this is a perfect example of that second rule. Water is water. Period. It doesn't matter if you get it from an iceberg in Antarctica, a river in the Amazon, or right out of your kitchen tap. The recipe, H2O, is locked in. It's always going to be 2 parts hydrogen for every 1 part oxygen. Every single time. The recipe is fixed. Okay, so we've got the rules of the kitchen down. Now it's time to meet the star ingredient. The one thing that everything is made of. It took until 1808 for a scientist named John Dalton to give us the first real scientific theory for this tiny building block, the atom. You have to understand, Dalton's theory was a total game changer. He proposed that, all matter is made of these incredibly tiny things called atoms. He pictured them as these solid, indivisible little spheres. He also said that all atoms of one element, like, say, gold, are identical to each other, but they're different from the atoms of another element, like oxygen. And the really crucial part? They combine in simple whole number ratios to make everything else. But that's the beauty of science, right? It's always updating itself. Dalton gave us an amazing starting point, but we've refined it since then. We now know that atoms aren't indivisible. They're actually made of even smaller bits, protons, neutrons, and electrons. We also know that slightly different versions of the same element, called isotopes, exist. But that core idea that everything is built from atoms, oh yeah, he absolutely nailed that part. It's one thing to talk about these little particles, but it's another thing entirely to try and wrap your head around just how small they actually are. So brace yourself, because this number is kind of mind-bending. The radius of just one hydrogen atom is about 10 to the power of -10 meters. What does that even mean? Well, to put it in perspective, if you could stack millions and millions of atoms on top of each other, the pile would barely be as thick as a single sheet of paper. They're just ridiculously, incomprehensibly small. Okay, so we have our rules, we have our main ingredient, the atom. So what's next? Well, now we get to see how they actually combine to create real-world recipes. How do we write the chemical formula for something simple, like table salt or water? First, we got to understand this key idea, the ion. An ion is just an atom with an electrical charge. See, atoms are normally neutral, but sometimes they can gain or lose these tiny negative particles called electrons. And when they do, they get a positive or a negative charge, which creates this attraction that lets them snap together. And there are 2 basic types. You've got your cations, which are positive. They're positive because they've lost one or more of those negative electrons. Then you've got anions, which are negative because they've gained extra electrons. It's that classic opposites attract thing. That pull between positive and negative is what forms a ton of chemical bonds. So how do we know how many connections an atom can make? That's where something called valency comes in. The easiest way to think about it is like this. Valency is the number of hands an atom has free to link up with other atoms. Some atoms have 1 hand, some have 2, some have more. It's their combining power. And check this out. Here's a really simple trick for writing a correct recipe. It's called the crisscross method. Let's try it with magnesium chloride. We write the symbols Mg and Cl.
Okay, magnesium's valency is 2 and chlorine's is 1. Now, you just crisscross those numbers so they become the little number, the subscript, for the other atom. The 2 from magnesium goes down next to the Cl, and the 1 from chlorine goes to the Mg. And boom, you get the balanced formula, MgCl2. Pretty neat, huh?
Now, this is all great in theory, but it raises a pretty huge practical question. If atoms are way too small to see, let alone pick up, how in the world do chemists actually measure them out for a reaction? It's not like you can just count them. The solution is this brilliant, absolutely essential concept called the mole. Don't worry, not the animal. Just like we use the word dozen to mean 12 of something, chemists use the word mole to mean a specific but very large number of atoms. It's basically the chemist's dozen.
So, just what is that magic number? How many tiny little particles are actually in 1 mole?
There it is, 6.022 times 10 to the 23rd power. It's called Avogadro's number, and it is a number so big it's almost impossible to imagine. Now, why that specific number? Because it's the perfect bridge. It lets chemists connect the invisible world of atomic mass to the very visible world of grams that they can actually weigh on a scale in the lab. It's ingenious. So, let's recap. We've got the rules of chemistry, we've got the ingredients, atoms, and we even have a way to measure them. Let's put it all together now and look at a few finished recipes from our cosmic cookbook for things you probably see every single day. Look at this. Here it is, all laid out. You've got water, ammonia, carbon dioxide, all very common things, and they're all built from just a handful of the same basic atomic ingredients. The only difference is the recipe, which atoms are used, and how many. Change the combination and the ratio, and you get a completely new substance with its own totally unique properties. And that really is the beautiful, mind-blowing truth of it all. The insane complexity of our world, everything from a tiny grain of sand to a giant star, and yes, even you and me, it's all built from a surprisingly simple set of atomic particles, all playing by the same elegant, unbreakable chemical rules. And that's a pretty powerful idea to leave you with, isn't it? If the building blocks and the rules of the recipe are the same for everyone and everything, then what is it about the specific arrangement of your atoms that makes you, you? That's something to think about.